Okay, so now we're going to start our transition into more complex circuits. Up to this point, in fact, let's do a quick review of that. We have looked at a circuit, a very simple resistor circuit that looks like this. So here's my battery. I have it connect over here. We can draw a switch in, and then we have a resistor over here. Okay, so let's check this out. So I'm going to try and build this in real life. I'm going to take a 100 ohm resistor. We've done a little bit of work with them. And let's see, do I have enough of my parts? Let's do this. Okay. That's fine. I should have enough supplies over here that I can build it. All right. So I've got a 100 ohm resistor. R equals 100 ohms. And let's find out what the potential difference is across our batteries. Now, this is without connecting the circuit, so in real life, they'll actually fluctuate a little bit. That being said, here's what I'm going to do. We're going to get a pretty good value for what we're dealing with. So I'm going to check here and here. Got about 3.18. Let's call that 3.2 volts. That's a potential difference across our battery, and therefore it will also be across this resistor because it's the only resistor in our circuit. Now, real quick, let's do a prediction. I'd like to know what the current coming out of the battery is going to be. That'll be the current that goes through the circuit and through the resistor there for Ohm's law. So let's see what we can end up with. All right. I built a switch in, and now that I think about it, I don't actually need the switch, but that's fine. I'm going to complete the circuit with my meter here. Let's see. I'm going to adjust this real quick. I'm pretty certain we're probably going to be safe. In fact, we know Ohm's law. Why don't we check? So I'd take 3.2 volts. So just as a quick reminder, we would have delta V equals IR. So if I want to find my current, it'll show up just like it does on the AP exam equation sheet as delta V divided by R. Divide both sides by R to get I by itself. So I would take 3.2 divided by 100, and I'd end up with 0.032 amp, which is, check that, 3.2 divided by 100, 3.2 divided by 100, yep, which is about 32 milliamps. So I retract my previous statement. This should be fine. I'm going to set it to milliamp, and here we go. I am going to set this up and get the following. I measure about 28.5, 28.6, so we're a little under 30 milliamp. Now, one of the things that I want to bring up on this is, and I mentioned it before, that when you have a battery fully connected, this one's a 5, yep. When you have a battery fully connected to what's called a load, in other words, onto a given, oops, let's see before I blow out my meter, set it to the right thing, potential difference. We can see that it drops a little bit. It's actually 3.1 volts. These wires are also, in real life, going to have a little bit of resistance of their own. In fact, I could check right here. That's not seeing anything. I'd probably have to bump it down some. That being said, we probably got a little bit of resistance. In real life, these numbers are going to fluctuate just a little bit, but we still get a pretty good value for what we're dealing with. All right. So that's a brief reminder of what we end up with here. We know that we're going to be off, give or take a little bit. It might be best for us to just kind of go to one significant figure. That being said, here's what we're going to talk about now. Up to this point, we've looked at circuits with only one resistor. And while that could be a pretty good representation of maybe a light bulb circuit, almost no circuits that you deal with are going to remain that simple. We need to start working towards more complex. So one of the things that we want to talk about is how we can deal with more than one resistor. And that ties into something called equivalent resistance. And we're going to work through and see what we can find out about equivalent resistance. But first, let's talk about what that phrase even means. Because what it actually is basically simplifying several resistors by imagining them as one resistor that acts exactly the same. So here's what we're going to do. We're going to look at several resistors put together into one circuit. Now, thus far, we've only been applying Ohm's law onto one resistor, and we're going to find that things are going to get more complex as we start adding more. That being said, one of our first steps to get to complex circuits is to, well, do what we do a lot of times. When we come up with something new and complex, let's break it down into problems we know how to solve already. So, equivalent resistance is going to help us take a complex circuit and turn it into a more simple circuit. All right, here's the one additional thing, though. We need to talk about this because when it comes to circuits, there are several different ways that we can add components in, and we need to talk about that. One is called series. Now in series, let's see, I'm going to draw these out real quick. So I've got battery. Here is an example of a series circuit. There's one resistor, and I put a second resistor in after it. I could draw this a slightly different way. This is going to be the exact same circuit that you just saw, although it will look a little bit different. I don't have to have them in the same line like this. I can have one here, one over here, one over here, one over here. And these are both series circuits. In fact, these two, assuming that the batteries are the same and all the resistors are the same, is an identical circuit. It also doesn't matter if this resistor is first or second. The order on this does not actually matter. The other way that we can set them up is called parallel. Now, parallel is a little bit different. Let me draw you some of those. So here is an example of a parallel circuit. They're side by side. Another great way of looking at this, I could redraw it. This, while it looks different, is exactly the same circuit. Resistor here, and I could draw one here. They do not have to physically be side by side. This is still a parallel circuit. All right, so take a look at those for just a moment. Hopefully we're going to get used to those because this is profoundly important terminology when it comes to adding components into circuits. How you add them will completely change what they do to the circuit. Circuits can be kind of complex, and the only way we can keep track of what's happening is if we keep a close eye out for series and parallel. Now you may be asking, okay, but you just gave me some drawings. Can you give me something a little more to go off of? Great. Let's introduce something that'll work for our functional definition for series and parallel. So let's go with series. Now, we're going to be looking at this in regards to resistors, but it turns out that this applies to components in general. When they're in series, this means that components in series are one after another in, I'm going to put in quotation marks here, a line. The reason that I have it in quotation marks is because, like you saw a moment ago, they do not have to literally be in a line. But I'm going to explain what this means as we go a little bit further. Now, what I found is this. One of the best ways to keep track of series versus parallel is the following. The current going through one resistor, or component, I should say, because this actually applies to all circuit components. One component must, at least in part, go through the other, the next component. So basically, if you have the current that goes through one of these things, go through another one, then those two components are in series with respect to one another. Now, it doesn't mean that all the current must go through. We're going to see in some of the complex circuits we're going to start to work with, we're going to see complex combinations of series and parallel. But if the current that goes through one of the components goes through another, then those two are in series with one another. Now, that's in stark contrast to parallel. Parallel has the following. Components in parallel are side by side. Now I'm going to put that in parentheses because, as we saw just a moment ago, they do not have to literally be right next to each other. But it's one thing that you can kind of keep an eye out for that may lead you to the right conclusion. In different branches of the circuit, they're kind of a two different path option. And that ties into the other thing. I find the ones in the green are my go-to ways of keeping track of this, though right now they may not mean as much to you. So we're going to take a look at the black definitions first, but as we develop this over the next couple of videos and lessons, we're going to see that the green is a much better way to keep track of this. The current, the charges flowing from the first one, or from one of them, from one, does not go through the other. Now, when I describe this, and we're going to see this as we go through, I want you to remember, in all circuits, for our purposes, it's a little simplistic, but it's still very good for what we're doing. All of the charges are trying to get from one side of the battery to another. So I complete this circuit. We have charges coming out of the battery, going over through here, through this circuit, and to the other side of the battery. I compared it to these charges rolling downhill. It's kind of like gravity. You don't normally have things rolling uphill. So that's why I say whatever path they're going to continually try to get from the positive end of the battery over to the negative end, because we are dealing with conventional current, where it is positive charge moving from high potential to low potential, from the positive side to the negative side. Great. I'm going to reference the green a lot more because it's my preferred way of identifying if you're dealing with series and parallel, but you got to learn to imagine where the current is going, and we're going to do that as we go forward. All right, now that we've introduced those, we can start to see what happens in equivalent resistance, where we take several resistors, many resistors, and replace them with just one resistor that acts exactly the same. And here's where we're going to play around with it some. Okay, so I've got my circuit kit here. I've got a 100 ohm resistor, and I'm going to do the simple approach, which is series. So here's what we've got. I'm going to have positive charges come out of this end. This is the positive terminal on the battery. Okay, sorry about the jump cut there. I was running into some issues with some of the equipment that I had set up. So we're going to go through and we're going to see how we can come up with this equivalent resistance. So I've got the following circuit. I'm going to have a supply, a voltage supply, basically a battery, that's going to come over here, and I've got two resistors that I've put in here. So here's my power supply. I was trying to work with some batteries, but I think they kept fluctuating some, so I've gone back to the source, a regulated DC power supply, which is going to give me a good solid output. And I've got it set right now to 3 volts. So 3 volts. And it should be pretty close to that because it's a nice regulated DC power supply. Here's what I'm going to do. We're going to go through, we're going to connect it with these two 100 ohm resistors. And we're going to find what current comes out of the battery. Now with that current, we're going to do the following. We're going to try and pretend, like I said, the equivalent resistance is taking several resistors and replacing them with one equivalent resistor that works exactly the same. Now I'm going to draw this out in green because I want to emphasize that it is not a real resistor. It's an imaginary resistor that acts the exact same. It's the equivalent resistance, so I'm going to call it Req. All right, here we go. We're going to find that by looking for the current, I, and we've got a potential difference across our source of 3 volts. All right, here we go. I've got it set to 3 volts. I'm going to turn this on, and I've got my meter set and ready to go. I'm going to connect here so that I can get my measurement. Oops. If you get a negative on these, it means that we've flipped where we want to connect them. I'm going to connect it here. So we've got it coming in through here. Let's see, red goes right into here. It goes through this, goes through our meter, and then we detect it. Why do I get a negative either way? That's not right. Okay, anyway. Let's see, that's fine. So my negative just means I've wired this backwards a little bit. I should have paid closer attention. That being said, we know that our current, it says negative 13.5, but it's actually 13.5 milliamp. And we're going to treat this as though it's an imaginary one. I'll flip the connections on this when I get a chance. It's 13.5 milliamp. Turns out, this is where that part that I said that we treated as positive current going one way, I've got my meter connected backwards, which means that it's going the opposite direction. Yeah, that's why it didn't matter swapping these, because this isn't the key part on that. That being said, when you're using these meters, if you've got a negative, you can just flip the leads usually, and that'll get you set up properly. So here we go. I am going to, yeah, that makes sense. That's why I need to connect this to this and this to this. In fact, we'll double check it real quick, though I'm certain it'll be the same. 13.5, maybe about 13.6. Maybe I got a slightly better connection there, but 13.5 sounds good to me. So we're going to put these in. We've got 3 volts equals 13.5 milliamp, which means it is 0.0135 amp. Remember, you must be able to deal with milli at this point, times REQ, the equivalent resistor that acts the same as these two 100 ohm. So let's find out. I've got 3 divided by 0.0135, and I get the following, 222. REQ for this equals about 220 ohms. Well, it's a little over 200. We've got some fluctuations here, of course. A little over 200, that means that, I've got 2 resistors. Maybe it just multiplied it by 2. 2 times 100 would get me about 200. Okay, let's try that out. Let's swap one of these out from a 100 to a 1000 ohm, and we'll see what it does. All right, now that I've got that, we've got this set back up again. In this case, I've now switched this to a 1000, and let's see what our new equivalent resistance is. Okay, our equivalent resistance, let's see. I'm going to connect this here and connect this here. I'm going to power it up. Here we go. 2.61, so 2.61 milliamp. That's what my meter is set to, so keep track of that. That isn't amp, it's milliamp. So that is move the decimal place 3 times. We're going to end up with 3 divided by 0.00261, that's amp, and I end up with the following, that my equivalent resistance is 1,150. Well, this is a 1,000 ohm resistor, and this is a 100 ohm resistor. Give or take a little bit, we saw in our Ohm's Law lab that while this says 100 ohm, it might actually be something like 110 ohms. And the other one might have been 110 ohms. Okay, and then our 1,000 ohm resistor might be a little bit more. It might even be upwards of 1,050 ohms based on its rating. Anyway, we can see we've got a much better idea of what's happening here. It looks like we're actually adding them together. Well, let's double check that. Here we go. I'm going to switch this out yet again. That's 100 ohm. Now I'm going to replace this with a 5,100 ohm resistor. All right, so our last one that we're going to take a look at is a 5,100 ohm. So let's do a prediction. It looks like we just add the 2 of them together. So our new equivalent resistance is going to be equal to 1,000 ohm plus 5,100 ohm. So we estimate somewhere in 6,100 ohm range. Okay, so let's see what we get. All right, I'm going to connect these. Clip, turn them on. I'm getting a current of 0.49 milliamp. Check. It's actually about 480 microamp. So let's go ahead and talk about the micro again. So in this case, we got a current of 482 microamp, which is going to be equal to 4.82 times 10 to the negative 4th let me double check. 6 and then 2, yep, fourth, amp. Okay, so let's go through and divide that properly. We've got 3 volts divided by, I like to use parentheses, 4.82 times 10 raised to the negative fourth, end parentheses, and I end up with the following. Our equivalent resistance on this one that we actually found is equal to 6,220, basically, ohms, which is very close to the 6,100. Remember, these are not going to be perfectly 1,000 ohm and 5,100. They'll have a little bit of what's called tolerance. We've seen that, at least with most of these, they appear to be a little high, which will explain why we're a little bit off there. All right, so takeaway message on series is as follows. I'm going to erase all of this. Equivalent resistance, if you connect things in series. REQ for series, one after another. We get the following. REQ is equal to R1 plus R2 plus ... We could have as many as you want, and if they're all in series, we just add them straight up. One final thing that I want to point out is, and I've mentioned it before, that order doesn't matter. It doesn't matter that I've got the 1,000 ohm first or the 5,100. If I turn this on, I get 482 microamp. If I switch these out, I might get something slightly different because I may have adjusted some of the electrical connections ever so slightly. We should end up with something in the 480 microamp range. Let's see. 482 microamps, so we're staying exactly the same. Order does not matter on which one comes first and which one comes second, because as charges move through the circuit, they're all moving together. Everything is happening at the same time. All right, I'm going to interrupt the video and be back with you so we can look at the parallel. All right, so now we're going to take a look at the same thing, except in parallel. So, in this case, we want them to be quote-unquote side by side. Here's what I'm going to do. I'm going to get rid of the 1,000 ohm and the 5,100 ohm, and I'm going to go back to the 100 ohms so that they're pretty similar, so that we can get an idea of what's going on with them, see if we can find some patterns. In this case, I'm going to have to get a little bit more creative. Here's what I'm going to do. Instead of putting one after the other, where the charges come in on one side and go through the other, out to the other side, here's what we're doing. We're setting them up where the charges are going to come in up here on this wire, and they'll be able to go two ways. Some of them are going to go through this path, and some of them are going to go through this path, and they're going to join up on the far side over here. So here's what I'm going to do. I'm going to set this here, and I'm going to take the other connection that I need to complete the circuit, and I'm going to put it here. So following through, we've got the charges are going to come out of the supply. They're going to go through the red wire. The red wire connects to the other red wire here. They go into my meter right over here, so I can count them, see what we end up with, and then they come out the far side of the meter, go through the circuit here. They're going to split off. Some of them go this way, some of them go this way, and then they're going to come back together to finish the circuit and go back into the power supply just like they would into a battery. We need a complete circuit or nothing happens. All right, here we go. I'm going to draw this out so we can see it in our circuit schematics. This is a parallel circuit. And a good way of looking at it would be something like this. One resistor here, and then another resistor in another branch. One branch here and one branch here. All right. We're going to have charges go through both of them. We've got 100 ohms for both of them in this case. And I've left it as a 3-volt source. Okay. Now we're going to do the exact same thing that we did before, and we're going to try and turn this into a circuit that we recognize and can easily apply Ohm's law onto. A single resistor circuit with some equivalent resistance. So it's going to have the same potential difference, which is 3 volts. And we're going to say that the current that we find that is coming into this circuit will be equal to the current that we will use for this circuit, so that we can take these two complex resistors and replace them with one equivalent resistor that we know how to work with. So here we go. 3 volts. I'm going to turn this on. We get 52.3 milliamp. 52.3 milliamp. 52.3 milliamp. All right, we go through and we find our equivalent resistance for this. For this very first one with the two 100s, we're going to find the equivalent resistance is, okay, so 3 volts divided by 0.0523. That gives me an equivalent resistance of 57.4 ohms. A little over 50, almost 60. Huh. We started off with two 100s, and we ended up with something close to 50, 60-ish. Hard to tell. Maybe it got cut in half. It got very close to getting cut in half. Maybe we divide it by however many branches there are. Okay, let's see. So here we go. I'm going to do, let's try a different number. Because again, it's nice starting off with the two same numbers, because then we can kind of see a relationship with the number that comes out, but it can make it hard to identify exactly what's happening here. Because parallel's a little bit trickier in how we can actually calculate that. With series, we just add them together, but clearly that's not what we're doing here, because we ended up with a smaller resistance. One resistor replacing these two is somehow even less than the two of them. Good to note. All right, here we go. Now I've switched it out where we've got a 100 ohm, and this one is now a 1000 ohm. So let's see what we get. In this case, we end up with let's use a different color to keep track of this. Our current this time is 30.2 milliamp. Our delta V is still 3 volts. So let's find out what our equivalent resistance is when we've got a 100 ohm and a 1000 ohm. So I take 3 volts divided by 0.0302, 30 milliamp, and I end up with a, interestingly enough, 99 ohm resistor is the equivalent resistance. Well, we'll come back to that. Okay. I'm going to replace the 100 ohm with a 5100. Great. Okay, here we go. Now I've got, and we'll use a different color for this one. Let's go brown. So delta V is going to be equal to 3 volts. Our current is going to be equal to, let's find out, 3.5 milliamp. I could get a better measurement than that, but let's just go with what we've got, 3.5. And that means that our equivalent resistance, in this case, is going to be equal to, let's find out, 3 divided by 0.0035, 857? I had a 1000 ohm and a 5100 ohm. In fact, let me draw that real quick. It looks like this. 5100 and a 1000. Now, real quick, I'm going to switch which one is in which spot. Once again, I tried to make the emphasis that order did not matter. Let's see if this has an effect. What if I switch them from one branch to another? Well, I'd just be swapping those two. Let's see. Nope, 3.5 milliamp. Okay, this one's a lot harder to actually figure out. So this is one where instead of us trying to figure it out just by looking at the numbers, I'm going to go through and give you the end result, and then we're going to double check it. All right, here we go. So, the way we keep track of series, or not series, parallel, the equivalent resistance for parallel, and this one's going to look a little bit different, 1 over Req equals 1 over R1 plus 1 over R2 plus ... These add reciprocally. In other words, we add them as 1 over. Let's double check. So on the very first one, we had 100. So I have 1 over my equivalent resistance equals 1 over 100 ohm. I'll turn this off. Plus 1 over 100 ohm. That gives me 2 over 100 ohm, which is, well, 0.02. Here's the thing. This is the most common thing that people mess up on. This is not equal to the equivalent resistance. It is equal to 1 over the equivalent resistance. That's why it ends up with over ohm. Ohms is in my denominator. I need to flip both sides. That means that Req is equal to 0.02 raised to the negative 1, which is the same thing as 100 ohms over 2. I flip REQ up, I flip B's around, and I end up with about 50 ohms, which is what we saw. It's actually about 57. Remember, these might be upwards of 110, and that might fluctuate it some. Let's take a look at the second one. We said that its 1 over equivalent resistance would be equal to 1 over 100 ohms plus 1 over 1,000 ohms. Okay, here's one of the parts where we're going to break off a little bit. 1, you can put this into your calculator. You can do 1 divided by 100 plus 1 divided by 1,000. And then remember, the answer you get is 0.011. That's not the equivalent resistance. That is 1 over that. So take 1 divided by answer, and this tells me that it comes up to 90.9. My equivalent resistance should be, according to my calculator, 90.9 ohms. We got 99, that's a little high comparatively. Again, there's a little bit of wiggle room on this, but we can see that we got kind of the equivalent there. The other thing that I will bring up is, this is a great point to be familiar with the rules for adding fractions. I need a common denominator, so I can turn this into 10 over 1,000 ohms plus 1 over 1,000 ohms, and that'll give me 11 over 1,000 ohms. So my equivalent resistance would be 1,000 divided by 11, which is 90.9. It's the exact same answer that I got from the other. So I could have my equivalent resistance on this is equal to 1,000 ohms divided by 11, which is about 90.9. Okay? I merely bring that up because a lot of times it becomes much faster if you can solve these things in your head or with a quick writing it down instead of plugging it into a calculator. That being said, either of those are good. Let's check our very last one here. We said that 1 over our equivalent resistance would be equal to 1 over 1,000 ohms plus 1 over 5,100 ohms. Now in this case, this is a great example of these numbers aren't particularly good for us to go through and try and do common denominators. That being said, I could do, what would that be, like 5.1? Yeah. Finding a common denominator on this one might be a bit more of a mess. To save some time and effort, I'll leave that for you if you'd like. We're going to end up 1 divided by 1,000 plus 1 divided by 5,100. And then I'm going to take 1 divided by that. We predict that we should end up with an equivalent resistance of about 836 ohms, which is not far off from the 860. Now, I apologize if the numbers are not working out perfectly, but you got to keep in mind, on the page, we're dealing with the nominal values. In other words, what the numbers are given to us here. In real life, these may not be 5,100 ohms. They might be a little above, a little below, and that's going to carry through with the result that we get. One final thing that I want to bring up, and we're going to talk about this when we start working with complex circuits a little bit more. When you are dealing with parallel, when you have a combination of resistors, and I'll point this out, 100 and 100, the equivalent resistance was about 60. When we had 1,000 and 100, the equivalent resistance was about 90. And when we had 5,100 and 1,000, we ended up with 800 some odd. When you have resistors in parallel, their equivalent resistance will always, always, always be less than any of the individual resistors. You will always end up with a number that is smaller than the smallest resistor that you have in that equivalent or in that parallel branch. When we start talking about how to interpret this in the advanced part of circuits, that'll become more clear as to why.